Hello everybody, and welcome back to page 109 in the workbook. And on this page we're continuing the discussion that we started in the preliminary example in the last video. Okay, so the second fundamental theorem of calculus just states in general the same observation that we just made. So let's refresh our memory what we noticed in the last example. Okay, so we started with the function a right here, okay, where a of x was defined as the integral from 0 to x of f of t dt. And what we noticed was sitting down here at the bottom of the page, okay, that it appears that f behaves like the derivative of a. Well, that statement can be turned around and said kind of the other way around, that a appears to be an antiderivative of the function f. And that's what the second fundamental theorem of calculus says. Okay, so let's read through this and fill in the missing parts. So if f is a continuous function and c is any constant, then the function a of x, defined by the integral from c to x of f of t dt, is the unique antiderivative of f of x that satisfies a of c equals 0. In other words, we could say that the derivative of that integral gives us f of x. Kind of the thing to notice here is that if you start in this situation, it's almost like the derivative and the integral are canceling each other out, and we're getting the function on the inside. Okay, let's illustrate that with an example here. Okay, so example 1 says, find a prime of x if a of x is defined as the integral from 1 to x of t squared dt. Okay, now this is a very short problem if we use the second fundamental theorem of calculus above here, because it just says if we take this derivative, then the derivative and the integral should cancel out and we should get the function inside. Okay, the only difference is that that t squared is going to turn into an x squared. Okay, so that by the second fundamental theorem of calculus. But we can confirm that statement that we just made using direct calculation. Okay, let's take a minute just to do that for this first example here. So if we took the derivative of a of x and kind of wrote out all the details, we'd start by saying we're taking the derivative of our function, which is defined like this in terms of an integral. And then we could take this expression and just kind of work through it step by step. Okay, so let's start with the integral from 1 to x of t squared dt. We know how to calculate an integral like that, so we'll just leave the d dx part there for the time being. So we need an antiderivative for t squared. So using the power rule, we're just going to get t cubed over 3. And then we need to evaluate that between the two limits of integration, which would be x and 1. Okay, and so as we usually do, next step is just to take those two limits of integration one at a time and substitute for t. So we'll start with x and plug that in for our t, and we're going to get x cubed over 3. All right, and then our lower limit is 1, so we'll plug that in for t, and we're going to get 1 cubed over 3. Okay, so we've got the derivative of x cubed over 3 minus 1 cubed over 3. So this d dx is just telling us, now take the derivative of what's in the brackets there. Okay, well, let's see if we can do that. So maybe just rewrite this first. Remember that x cubed over 3 is really just the same as 1/3 x cubed. And I'm going to go ahead and simplify 1 cubed over 3 as just 1/3. Now let's see if we can take the derivative of that. So starting with the 1/3 x cubed, the 1/3 is a constant, so we can kind of just factor that aside. And the derivative of the x cubed part of that, just by the power rule, is going to give us 3x squared. And then we come to the minus 1/3. What would its derivative be? Well, minus 1/3 is a constant, and so when we take its derivative, we're just going to get 0. It just goes away. So all that we're left here then is 1/3 times 3x squared, and notice that the 3's cancel, and sure enough, we get x squared. That's the same answer that we got up here. We just confirmed what the second fundamental theorem of calculus said by direct calculation.